Analysis of graphs and functions. In this session, we'll take a look at vertical and horizontal shifts of graphs. We'll look at stretching and shrinking of graphs, and also reflecting graphs about axes. First, we'll take a look at vertical shifting of a graph of a function. If c is greater than 0, which means that if c is positive, the graph of the function y is equal to f of x plus c is a shift upward of a distance of c units. Likewise, if y is equal to f of x minus c, the graph is a shift downward a distance of c units. Let's take a look at an example. Here we're asked to graph the function y is equal to x squared. So I'll simply graph that using my graphing calculator. I'll go to y equals and I'll place in x squared. I'll use zoom 6 to graph initially. And notice we have the graph of a parabola. Next, we're asked to shift the graph of y equal to x squared up by a distance of 2 units. So following the formula, I'll simply add a constant of 2 to my squared function. So I'll go back to y equals, and in y sub 2, I'll simply put in x squared plus 2. I'll scroll to the far left. I'll click enter one time, and it will now graph a thick line, and this is so I can distinguish the two lines. And now I'll regraph, and you can see that my initial graph was shifted upward by a distance of 2 units. So my equation here is y is equal to x squared plus 2. And this will shift my graph up a distance of 2 units. Next, we're asked to shift the graph of y equal to x squared down by 2 units. So I'll simply subtract the constant of 2 from my squared function. So I'll go back to y sub 2. I'll simply change my addition to a subtraction. And if I regraph, notice that my graph has been shifted downward by a distance of 2 units. Therefore, the equation for my graph is y is equal to x squared minus 2. Next, we'll look at the horizontal shifting of a graph of a function. If c is greater than 0, then y is equal to f of x minus c is a shift right c units. Likewise, if y is equal to f of x plus c, then the graph is a shift left by c units. Once again, we'll graph the y equals x squared function. We have our basic quadratic function. Now we'll shift the graph of y equal x squared to the right by 2 units. And if we use our formulation, we should enter in our function as parenthesis x minus 2 in parenthesis, and now we'll square that quantity. And if we graph, notice that our graph is shifted to the right by a distance of 2 units. Therefore, our equation for the graph that's shifted to the right by 2 units is y is equal to x minus 2 quantity squared. Next, we'll shift the graph of y is equal to x squared to the left by 2 units. So in this case, we'll simply add 2 to our x variable quantity squared. Now if we graph, we see that the graph is shifted to the left. So our newfound equation is y is equal to x plus 2 quantity square. Next, we'll vertically stretch a graph, and if c is greater than 1, then the graph of y is equal to c times f of x is a vertical stretch. However, if c is greater than 0 or less than 1, then the graph of y is equal to c times f of x is a vertical shrink. Here again, we'll take a look at the function x squared. So we have our quadratic equation once again. Now we'll vertically stretch the graph of y is equal to x squared by a factor of 2 units. So for y sub 2, I'll now enter 2x squared, and I'll regraph. And notice that we have a vertical stretch by a factor of 2 units. So our newfound equation is y is equal to 2 times x squared. Next, we'll vertically shrink the graph of y is equal to x squared by a factor of 0.2 units. Keep in mind that we're multiplying our function by some number that's between 0 and 1. So I'll go back to y sub 2. And I'll regraph 0.2x squared. And notice our vertical shrink on the graph. And our newfound equation is y is equal to 0.2 times x squared. Now we'll horizontally stretch and shrink a graph. It says that if c is greater than 0 and less than 1, then the graph of y is equal to f of c times x is a horizontal stretch. Likewise, if c is greater than 1, then the graph of y is equal to f of c times x is a horizontal shrink. So once again, we'll graph y is equal to x squared. And note our parabola. Next, we'll horizontally stretch the graph by a factor of 2 units. So I'll go back to my y equals, and now I'll put in 2x, and I'll square that quantity. And notice the graph, we have a horizontal stretch. So our newfound equation is the quantity 2x squared. Next, we'll horizontally shrink the graph by a factor of 0.2 units. So I'll go to y sub 2 once again. And I'll change my value for c to 0.2, and I'll regraph. And notice our horizontal shrink. So our newfound equation is y is equal to the quantity 0.2x squared. Next, we'll reflect the graph across the axes. And in order to reflect the graph across the x-axis, we'll graph y is equal to negative f of x. And in order to reflect the graph across the y-axis, we'll graph y is equal to f of negative x. In this example, we're asked to graph the exponential function y is equal to e raised to the power of x. So in my y equals, I'll graph my exponential e function. And notice the shape of the graph. Now we'll reflect the graph of y is equal to e to the x across the x-axis. So notice, in order to reflect across the x-axis, I'll simply multiply my function by a negative. So I'll simply go to y sub 2, and I'll enter in a negative e raised to the power of x, and I'll regraph. And notice that our graph is reflected across the x-axis. Next, we'll reflect the graph across the y-axis, we'll simply graph y is equal to f of negative x. In order to find f of negative x, I'll simply go back to my function, and wherever I see an x, I'll put in a negative x. So in order to reflect the graph of e to the x across the y-axis, I'll enter this into my calculator as e raised to the power of negative x. And notice that our graph is reflected across the y-axis. And that newfound equation is y is equal to e raised to the negative x. Thanks for watching.